please.
Good afternoon, everybody. My name is Antonio Pellegrino. I work at the Impact Engineering Laboratory at the University of Oxford. And today my topic, I think I need something else. Okay. Today my topic is the definition of the RVE for granular materials to be specimens to be tested on the Hopkinson bar at Einstein rate. My talk records the following steps: possess motivation, the variation of the weight ratio within test samples, the estimation of the smallest RV for uniaxial compression experiments at Einstein rate, and some experimental results proving the validity of the method we propose. So first of all, why do we care about the behavior of sand at Einstein rate? This behavior is of great interest for defense and quarrying industries. Of course, if you want to protect your soldiers behind a wall of sandbags or underground bunkers, you need to know the behavior of granular materials like during penetration of bullets, and hence Einstein rate behavior. Same thing if you want to study mine explosions, earthquakes, and volcanic explosions. And also, from a more peaceful point of view, in the field of oil and gas, this behavior at elevated speed of deformation gives information on the drillability of rocks and on the wear and tear of drilling tools. Of course, it's also widely used in civil engineering, maybe not at Einstein rate. Where do we start from? We start from the variation of the weight ratio within test samples. Granular materials are, of course, highly heterogeneous, and their mechanical properties depend on a number of parameters, like initial consolidation state, confined pressure, moisture content, strain rate, intergranular friction, and grain shape. Of course, as any discontinuous material, every material is discontinuous. There is a certain volume, a representative volume element at which we can consider the material as a continuum. And this volume should provide information on the microstructure, at the same time represent the mechanical behavior of the macroscopic body. So once we define the type of sand and the type of test we are carrying out, we define all the parameters that are underlined in the black box. So confined pressure, moisture content, strain rate, grain shape, and intergranular friction. The only parameter that needs to be controlled is the initial consolidation state. Indeed, as is shown in the diagram on the lower right end of the page, the very same material will show a very different result if the initial consolidation state is different. And this parameter has to be taken into account in the definition of the RV. Otherwise, the scatter of the experimental result will be so high that we are really not testing the same material. The parameters we describe in this consolidation state are usually two: the void ratio, volume of voids divided by the volume of solids in a sand specimen, and more usually porosity, volume of voids divided by the total volume of the specimen. They are easily related by simple algebraic equations. Very important for dynamic testing is the stress wave propagation speed, because this one is very low for granular materials. It is common practice to reduce the aspect ratio of the specimen at very low values. But as we will prove, this is not always possible because there is a lower limit imposed by the RV. So how do we evaluate this? We start from analyzing the variation of the weight ratio within the samples. We do this using discrete element simulation, using geometrical packing algorithms, and estimating the void ratio within the sample with the same size distribution of the sand we are going to test. We do this because in the vicinity of the walls and on the free surface, the particles forming the material, they organize in a different manner. So close to the wall, we will have more organized particles, and close to the free surface, we will have a lower, higher void ratio. Let's imagine this is a sand sample, and well, here is in 2D, but this approach is, this estimation is done in 3D. And these particles are simulated according to the real size distribution of the sand. And let's imagine we build progressively larger boxes, starting from a very small virtual box to a box equal to the dimension of the sample. And with this approach, we calculate the volume of solids and the volume of voids within these virtual boxes. What we find is that for very small virtual boxes, the volume of this virtual specimen is comparable to the volume of the single grain. So the void ratio can be very discontinuous and very low. And this is, do we have a pointer? Oh. This is the zone 1 in this diagram. Then, as long as we increase the parameter d, we find a plateau area where the effect of the walls on the free surface is not present. So this is the area we care about when we define the dimension of the specimen. Then in the zone with very large boxes, then we'll have a higher void ratio because the effect of the free surface takes over. Now, how do we exploit this in the definition of the smallest specimen we can use? Of course, we would like to have this specimen as small as possible to achieve better dynamic equilibrium conditions. So we use an iterative process. I must stress that this process has to be repeated every time we use different bars and different materials, and of course different sand. So we start with the choice of the apparatus, of the emitter of the Hopkinson bar. And we start with an exploratory number of particles. Then, starting from that, we run a number of discrete element simulation in similarity with what we do when we do experimental tests and we prepare our specimens. And at this stage, at the end of the simulation, the length of the specimen and their aspect ratio is defined. After that, we compute with the procedure we have just explained the variation of the void ratio within the specimen. And we analyze the zone 2 of the diagram. So in this area of the virtual boxes where they are not too small but not too close to the walls. Then we look at if there is any significant scatter in the plateau area, and if the plateau is very well defined. If not, then the volume of the specimen is smaller than the RV, and we need to increase the number of particles. This process will stop only when the plateau area is very well defined and the scatter is insignificant. Then we know we are sure the volume we are taking into account, and hence the number of particles and the aspect ratio of the specimen we're going to use is greater or equal or greater than the RV. And now is the time to see if check if the method works. So conduct some experimental results on the Hopkinson bar. What we did is we use a compressive Hopkinson bar provided with a very long projectile and stress pulses of around 1.1 millisecond. And we enclose the sand in the latex confinement for quasi-uniaxial stress condition and steel confinement for quasi-uniaxial strain conditions. Under dynamic equilibrium conditions, the stress time history is proportional to the portion of the wave that is transmitted to the specimen, and the strain rate history is proportional to the reflected wave in the input bar. We have also defined two repeatable experimental procedures to prepare loose and dense specimens, which I'm not going into detail. And we tested a number of different sand, from Euro-quartz sand with some sub-round grains, Q-rock polyhedral grains, and Etnian sand, characterized by angular grains with vesicles and inherent porosity, and also another Skling-Meyer sand characterized by subangular grains with a narrower range of dimension between 0.4 and 0.8 millimeters. The results prove that they are quite repeatable, proving that we are indeed controlling the initial consolidation state. And here we are showing some results on loose Euro-quartz sand in a rigid confinement, stiffer response, and deformable confinement. On the right-hand side, we can see what happens to the confinement during the Einstein rate test. And then we have compared the response of different sand at Einstein rate and closed in rigid confinement and at the dense consolidation state. And we can see there is a clear trend. The round grains like Euro-quartz are behaving in a stiffer manner compared to rock and Etnian sand. So if you need to protect your solder behind sandbags, then you better use rounded grains. In conclusion, a numerical procedure for the estimation of the smallest specimen dimension has been developed. And this procedure is based on the void ratio in the specimen and was tested on tests conducted on the split Hopkinson pressure bar apparatus. And the reproducibility of the results, reproducible results, prove the effectiveness of the method, because we are indeed proving that we are controlling the initial compaction of the specimen. Future development will include analogous procedure for wet sand, high temperature testing of silica and volcanic sand rocks, modeling of ballistic penetration and blasting of silica and volcanic rocks, sand pinning on titanium alloys, and silica and volcanic sand deposition on hot nickel superalloys for ingestion in jet engines. That is everything. Thank you for your attention.
You have a question? Okay. I have some question related to how to consider the